All right, chapter 16, second to last chapter. On these next few chapters, we talk a lot about waves. This mostly focuses on waves. The sound part of waves generally is the later parts of chapter 16 and on into 17. This is a picture of a cylindrical cloak for water waves. We have been able to cloak certain types of waves. We can cloak very small objects at, say, the infrared, i.e., heat signatures. They've also built a macro scale, so something you can actually see sized cloak for water waves. This isn't really big. It's got like I mean, it's small. Where'd my pen go? But this little cloak is I think it's around 10 centimeters. So it's actually sizable. But basically, it proves to be invisible to water waves by using, we haven't talked about this yet, diffraction to diffract around the object, thereby making the object itself invisible. Other than being cool, the idea is that you want to use this to build it up even larger, and you can diffract, say, tsunamis. And you can maybe deploy it to a certain area or the size of a town, and it can literally diffract the water waves around a certain area of our town, or you get the picture. As of now, they still cannot cloak anything in the visible light spectrum, so we can't really go invisible, but there are other ways of cloaking. So that's your kind of intro to waves. It's the first time we can actually see something. Granted, with water waves, we can still see it. All right, nature of waves. Basically, a wave is a traveling disturbance, whether it is through the air, a sound wave, space, an electromagnetic wave, water waves. Essentially, it's not purpose, but one of its main byproducts is it carries energy from one place to another. A tsunami would carry energy from somewhere deeper in the ocean to the shoreline. There are two types of waves. You have your longitudinal and you have your transverse. Let's start with transverse because that's the traditional wave-like feature. Basically, it's the woo, 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 that one. Oh, you know what I could do? You know what I could do? You know what I could do? Yeah, I can do that. Ha! Look at me go. All right, so that's your transverse wave. The disturbance is perpendicular to the direction of the movement. So we perceive the wave to be moving this way, but the disturbance is going perpendicular up and down. That's transverse. That's like if you have a piece of jump rope and you're jump roping with some little kid and you just start waving it up and down. Usually I show you this with a slinky with both types. Can't really do that now. Well, I could, but I don't really have that great of a way of filming myself. Not that I know of. And I don't know where my slinky is. That too. Now, longitudinal is a slinky. So let's say you have a slinky. Let's do this here. Wee, 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 doo, doo. Oopsie. And then we have do. Okay, not a great slinky. But, so you can imagine a slinky moving back and forth. And this little portion right here we'll talk about later is your amplitude of the wave. But you could kind of view this little smaller portion in the slinky moving to the right. So the disturbance is in the direction of the movement. These are sound waves. Sound waves are an example of longitudinal. Whereas transverse wave is like electromagnetic waves, so light, so EM waves. And those are your two main types, longitudinal and transverse. All right, so the anatomy of a wave. All right, so here's my picture of a wave. A couple things to note about this. Let's see here. Lambda is your wavelength. I think we've talked about that before, but if not, I'm going to go over it again. This is a lambda. Lambda. It stands for wavelength. And your wavelength is either going to go from peak to peak, trough to trough, or equilibrium to equilibrium. And so that's your wavelength. It's got to have one full cycle. So in this case, it starts at the very top, goes all the way down. That's half a wavelength, comes back up, and once it is ready to start the cycle again, it's completed a wavelength. We've talked about period before, but period is basically the time to take one rotation. And so it starts here, goes through. Here it's only half of a period because it's kind of reversed around. And then once it comes back down again, we have a full period. Amplitude, we've kind of talked about. Remember, that's displacement from equilibrium. So that'll be the measure from this equilibrium line to the top. This is my equilibrium line, by the way. Equilibrium. We'll pretend I spelled that right, because I can't remember. And also this would be your amplitude down here. It could be above or below. That looks like IA, but you get what I'm saying. Amplitude. Frequency is 1 over the period. Frequency is measured, if you recall, in hertz, or it's basically a 1 per second. So if you listen to the radio station and you listen to 95.1, that's 95.1 megahertz. So that means it's cycling 95.1 million times every second. So that's what you're tuning into. The velocity is the frequency times the lambda. And this makes sense because frequency is going to be 1 over a second, and then this is a meter, and so that gives you a meter per second, which is the proper unit. I always say V equals lambda, F lambda, lambda. Kind of sounds like a filet mignon, but not quite as tasty. But anyways, V equals F lambda. And when you get to physics 2, you'll see this again, but it'll be C is equal to F lambda or something very similar to that, where C is the speed of light. More on that in physics 2. So, all right, so those are the things you need to know about a wave. Let's do a problem. All right, let's say you have a wave. It travels at 3 meters a second, so there's our velocity, and crashes against the shore every 11.5 seconds. We want to figure out the period, the frequency, and the wavelength. So every 11.5 seconds, a cycle occurs. That means the period is going to be 11.5 seconds because that's how long it takes to cycle over. Frequency, if you recall, is 1 over the period. And so if I want to figure out frequency, I'm going to come down here so I don't run out of room. I just take 1 divided by my 11.5 seconds. And if I put that into my calculator, I'm going to get F equals 0.0, it looks like 87 hertz. So that's my frequency. That means it's making 0.087 cycles every second. So it's not making a cycle every second. Way slower than the 95.1 you might be listening to, or I don't listen to 89.1 KMUW. Still 89.1 million cycles a second. But that's the frequency of, say, this wave right here in Tasmania on a beach. It was a nice beach. Tasmania. It's a good place. Wavelength. Wavelength. Okay. To get wavelength, we're going to have to use V equals F lambda because we know V is going to be 3. And now we know our frequency is 0.087. And I'm going to write 1 per second on this case. And then lambda solving there. So I'm going to take my 3 and I'm going to divide that by 0.087. And I'm going to get my 34.5 meters. So definitely a water wave. It's going to have a wavelength this long. Large water wave at that, but either case, 34.5 meters. And then notice your seconds over here is going to cancel, leaving you with a unit of meters, which is what you wanted to begin with. Yay! All right, the speed of a wave on a string. The ability of one particle on a string to pull another particle is affected by the tension on the string. Kind of what that means is the tighter your string is, not really necessarily the tighter string, as I'm getting ahead of myself, but the tension in your string has an effect on how fast the wave travels. And I think I could kind of show you that. Give me a moment here. I have something over here. Can I vary the tension? I thought I... Oh, I can. Ha 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 ha. Okay, so I want to take out the dampening here. So this is high tension and this is low tension. And the tension matters. I mean, clearly you can see when there's low tension, we have a higher frequency and a shorter wavelength, which are inverses of each other. And then if I move to medium tension, then when, it gets a little bit less frequent. And then the high tension, we get a larger wavelength and a much lower frequency. So tension clearly has an impact on the wave structure. Going back to this, additionally, the more massive a string is, the slower the wave should move. So mass matters. Basically, material, what it's made of, that's a really bad aerial, there we are, it affects your speed. Your material will affect your speed. I don't think this simulation gives me... No, I can't change it at all. But just have to take my word for it. Material will affect speed. And then that leads us to, and this is more of an experimentally... Well, it's not really experimental. There's a proof. It's kind of beyond the scope of this class. We get V is equal to F over mu. Mu is the linear density. It's the mass of the string divided by the length of said string. Your book says V is equal to the root of F over M over L, which I guess is fine too. I use mu because it's a little bit more, I feel like it's more standard for linear density, but either way it's the same thing, but I just say mu for linear density. And linear density is the mass of the string divided by its whole length. Obviously that's how you get density. And it's different than volumetric density, which is the mass divided by the whole volume. So it's just density in one dimension, one-dimensional density, so to speak. One thing to note is that the velocity of the particle, and I'll go back to the PHE simulation on this, the velocity of your particle is not equal the velocity of the wave. So going back to the PHET simulation, the velocity of the particle or the wave is the speed of the wave as it's moving to the right. Basically, the ocean wave I just did an example on. That's the velocity of the wave. The velocity of the particle is, if you just note, let's slow this down. There's a slow, there you are. Is literally the speed of this particle as it moves up and down. And clearly, since it's going up and down, that speed is going to be vastly different than if I were to track this across and see the speed of the wave. So the speed of the particle and speed of the wave are in two different dimensions. One's perpendicular and one's horizontal. Mathematically speaking, if you recall from chapter 10, your A omega sine of omega t is not equal to the root of F over mu. Does not equal. They're not the same thing. So we're finding, when we did this in chapter 10, we were literally examining, where did you go? This little green particle going up and down. And all of our equations were based off of that to describe the motion of the back and forthness of that green particle. Now when we talk about wave speed, we're actually talking about, like, if I just kind of track this wave crest as it moves to the right. So two different things that we're doing now. That's why everything seems to be different, is because we're looking at the wave as it moves horizontally, whereas before we looked at the wave as it moves vertically. More or less. Kind of depends on the type of wave, but conventional waves, that's what we're doing. All right, so let's see here. That's all we need to know on that. We'll do a problem. Let's say the tension of a 34 kilogram power line is around 19,000 newtons. These are legitimate numbers. I looked them up. While the poles are spaced around 38 meters apart, also pretty, somewhat standard, I believe. A small squirrel jumps on a tree and lands on a power line. What is the resulting velocity of the wave? Neglect the force due to the squirrel jumping. Pretty simple. We're just going to use my V is equal to F. And since they give us mass and length instead of mu, we're going to do mass divided by length. and I literally just have to plug in what I got. So your tension, you don't need to do like 2 times 19,000 since there are 2 poles. That has nothing to do with it. It's just the tension that's actually measured. And so you'll write it as 19,000 newtons. And then the mass is going to be 34 kilograms. And then we know that it's 38 meters apart, so we're assuming it's 38 meters. All right. 19,000 divided by 34 divided by 38. And then rootified, I get a really fast speed of 145 meters a second. 145.7 meters a second. And that's the speed of my wave as it moves horizontally from that squirrel. All right, so this is usually pretty simple. It's just literally plugging it in. Maybe one of your homework problems a little bit more beyond that, but not that much more. I went ahead and drew these pictures because it took me forever. Otherwise, you just watch me drawing it. But the nature of sound. So this is right here is a speaker. It's the best speaker I can draw in the world. Speaker. And a speaker will output sound. When it outputs sound, if you were to look at it on, let's say, small scale, super small scale, for lack of a better word, you would see a couple things. You would see, and I told you this is a longitudinal wave, and it is for sound. It will give off what's called a condensation. The condensation is basically when all of your particles are together. When that speaker produces a sound, it produces a condensation, which and you could feel it next to a speaker. You could feel it outputting a little bit of oomph. Well, that little bit of oomph creates that condensation. And if we just track it moving to the right, that condensation, here's one here, and here's another condensation here. So it's like boom, 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 So it's moving to the right. And so basically, if you look at it from the very small scale, you can see the condensation, and you can see that condensation continuing to move to the right. And if you note the difference between the two condensations, you can get wavelength, and you can get all sorts of information from that. Over here, where there's space normally, this is normal air pressure. So what we have is your condensation is moving into your normal air pressure, essentially, collapsing and expanding your air as it moves until you hear it in your ear. That's why I have a 1 there. Now, 2 is a few seconds, micro, probably just milli, but let's cover all our bases, seconds later. So a few seconds later, your condensation, this is something, I think we get to this, it's called your pressure amplitude. It's moving to the right, and it leaves this kind of voided area of a lower air pressure, and that voided area is called the rarefaction. So that little area, and it kind of helps you notice and be able to discern the different types of sounds that you're hearing, and as opposed to just white noise. And so you have a couple things to get out of this. You got condensation and you have rarefaction. So that's what I talk about condensation, I talk about rarefactions. That's what these are. Up here kind of explains it more mathematically. If a diaphragm, and this is the diaphragm right here, is basically the edge of your speaker. If it completes 1,400 oscillations per second, then what that means is your speaker is producing 1,400 condensations, and they're created every second. And we measure that to be 1,400 hertz. And we'll talk about different types of sound waves, I think, next chapter. But that's how we can measure your sound waves. So if you're hearing, saying 1,400 hertz is on the low end. Low, high end, sorry. Thinking about something else. Low end would be like 400 hertz. But 1,400 hertz would be a high pitch. I'm kind of getting ahead of myself here. In any case, when you hear that sound, that hertz sound, that's telling you how many little condensations, or rather pressure amplitudes, you have per second. And then I have one that I've actually drawn out ahead of time, or rather created. And I talked about pressure amplitude of the sound wave. So this little area, this condensation, that's what's called your pressure amplitude. So it creates that little tiny little pressure amplitude, and that pressure amplitude moves to the right, um, and it can kind of give you areas of high pressure and low pressure. Because when you hear something, you're hearing a small, minute pressure differentiation. And that pressure differentiation is how you perceive it to be sound, more or less. So you'll have regions of high pressure and you have regions of low pressure. When I pause, then you hear less. That's when your region of low pressure is when I pause. High is when you're hearing my voice. If we are to graph that, we see high and low areas. The pressure amplitude is essentially your amplitude. So when I talk about pressure amplitude, that's your little condensation, and that is the actual amplitude of your wave. That's why we have noted over here condensation. It is the pressure amplitude. The rarefaction, oopsie, I do that all the time. Rarefaction, I always want to say rarefaction. It's rarefaction. Never gotten that through my head. Some things I can't, to this day, I still say in my head, NES day for Wednesday, because I can't spell it. In any case, that's a rarefaction, and that's the trough of your wave, whereas the condensation would be kind of like your peak, or your ridge of the wave. Speed of sound. Told you we would get here, and well, we are here. And I kind of mentioned this before, but the denser the material, the faster the sound will generally travel in that material. Sound will travel much faster in water than it does in air. Also, it'll travel even faster in a solid, like a metal pipe of some sort. The speed of sound in air is around 343 at room temperature, and it does vary based off of temperature. And how does it vary? Well, there's an equation for that. For an ideal gas, we have V is equal to gamma kT over M. This gamma is the ratio of the specific heat capacity of constant pressure to the specific heat capacity of constant volume. And if you recall, it's going to be 5/3 for an ideal monatomic gas, and 7/3 for an ideal diatomic gas. So that's kind of a fixed value the whole time. M is going to be the mass of said gas. And T, of course, is going to be temperature, and K is your constant. So let us do a problem on that. All right. I'm taking liberties on this problem, and I'll go over that a little bit. Let's say you're at a height of 8 meters above the surface of Berkeley Pit. It's this pit in Montana, I believe. And it's full of toxic metals and water, or what resembles to be water, which we're going to assume is going to be kind of gassy in this case, hence the taking liberties. But it's really unique because they have to employ different techniques to keep birds from landing, otherwise they get fined because birds will die once they land on that surface. Sometimes they have a guy on a rowboat with a shotgun, but they've employed various different techniques to try to keep the birds out. But it is heavily dangerous. Heavily dangerous. Heavy metals, very dangerous. There we go. Anyways, so let's say that you're above it and you have like some sort of sonar, which utilizes the equation we're going to use, and it sends out a pulse, and that pulse hits the water, goes all the way down and comes back, and it takes a period of 2.64 seconds. We're going to assume that the air and water temperature are 25 degrees Celsius. We're going to figure out the depth of the pit. We're going to assume that whatever's in there is gaseous, kind of gas, watery, gashery. It's not, but we're going to assume it for this case. Plus, I wanted to use a sonar type example, so that's why I'm doing this. And we're going to assume it's diatomic and its mass is 33U. Let's first figure out what 33U is in kilograms. So I take 33U, put it over 1, and then I know that it's 1.6605, I always forget that last digit, according to the book, times 10 to the negative 27th kilograms, and that's per U. And when I put that into my calculator, I get 5.48 E26, and that's my mass. E negative 26. Sorry. Okay. Let me kind of draw a picture of what's going on here. We're going to assume that the sonar pulse is emitted by some high-tech bird. And it's going to emit a pulse. Let's put it over here. And then it's going to hit a water surface. Look at me being all watery. Water. And then it's going to keep going before it hits the bottom of a pit. And it's going to go back up and return to the bird. So it's going to go down this way, up this way. I know a couple things. This I'm going to call Y1. That's the distance from the initial sonar pulse to the water. And then the depth of the water we're going to call Y2. We know that it's going to travel in Y1 and in Y2 twice because it's got to go there and come back. So when you send out a pulse like for sonar and you're using it to calculate, you got to be aware that it's going back and forth. And we will take that into account. I know that T tot is equal to 2.64 seconds for the time. And I know that T tot is going to be, the total time is not only going to be T1, but it's going to be twice of T1. So twice to traject this Y1 area, plus 2 times T2. Okay, that doesn't give me anywhere near getting the depth, which I'm aware of. But I do know a couple things. I know that it's a constant speed that we're talking about here. And I know since it's a constant speed, it's simply going to be y over v. So we just take the distance and divide it by the velocity and we can get time. So if I take that into account here, I take t tot is equal to 2y1 over v1 plus 2y2 over v2. This is a bit more workable. We know what t tot is. We also know v1 is the speed of sound in air because y is inside the air. Inside is in air. You get what I'm saying. So we have that value, but we don't know y1. We don't know y2. Actually, we do know y1. I'm sorry. But we don't know y2 because this height right here is 8 meters. So we're going to solve this for y2. But I'm going to make one more substitution before I do that. Even though it makes it messier, I think it makes it more clear. And that is we have 2y1 over v1 plus 2y2. And I'm going to use the equation given. The gamma, the Boltzmann constant, temperature divided by my mass. And that, now I can go ahead and solve this for y2. And I'm going to do that. So I take my t tot and I subtract my 2y1 over v1. And then that's still equal to 2y2, over the root of gamma kt over m. And then I'm going to multiply by the bottom and divide by the top here. And that's going to give me gamma kt over m times t tot over 2 minus y1 over v1, where I've already distributed the 2. So I multiplied by that and then divided by 2, but this one had a 2 in it already, so it ends up being a little bit simpler. Maybe I should use x instead of y's. These y's are really funny, but whatever. All right, I can plug in numbers. Yeah, it's going to be a lot. Let's do that. Okay, we said it's diatomic. So according to that, we would use the gamma as 7/3. All right, so let's start with that. So we have 7 over 3. Our Boltzmann constant is going to be 1.38 times 10 to the negative 23rd joules per Kelvin. And then temperature was 25. 25? Yeah. So we got to change that into Kelvin, so that's going to be 298. I kind of forgot what it was. All right. and then over m, and that's why I started off with a mass, because I didn't want to have to go back and convert it. 5.48 times 10 to the negative 26 kilograms. That doesn't need, it looks like 266. That was supposed to be a kilogram. Well, let's just leave off the units, because that's even making it worse. All right, that is, crap, forgot already. 5.48 times 10 to the negative 26. All right, and then that was just outside of my parentheses, but it won't be as bad here. T-tot was 2.64 seconds divided by 2. And then minus y1, we decided was 8 meters. And the speed of sound in air, roughly at 25, is going to be 343 degrees. Sorry, 343 meters a second. Make sure I'm right. Yeah, 8. Okay, that's all going to equal y2, by the way. So now I'm going to plug in my calculator. All right, 7 divided by 3 multiplied by 1.38 times 10 negative 23rd times 298. Divide that by 5.48 times 10 to the negative 26. And then I take the square root of that. Okay. Oh, and then I'm going to multiply that by 2.64 divided by 2. And I'm going to, oh, that made it really messy, in my calculator at least. All right, then I'm going to subtract. It was 418, what was inside the entire square root there, 418.4. And I'm going to subtract the multiplication of that times 8 divided by 343. And I get 542.5, which I think is the actual depth, because I think I looked that up when I originally did this problem. All right. So anytime you use some sort of like sonar or some, echolocation for a bat, you got to factor in that it's going to be twice the distance, because you're going to send out a pulse, it's going to bounce off something and come back, and so you always have to factor in that it's going to be a there and back type situation, which is why we had to do the 2 T-tots, or the T-tots and the 2T1, 2T2. Anyhow, I think you have one problem, if I remember correctly, in your homework, kind of like this, which is why I took a lot of liberties, but I kind of like the pit. It's kind of cool. All right, so I mentioned earlier that, yeah, it's technically water, and water doesn't behave as a gas. It's kind of got its own equation. Yeah, it does. The speed of sounds in liquids and solids has definitely a different equation, and it depends upon it's the bulk modulus or the Young's modulus, if you can remember back to chapter 10. Also, it depends upon the density. So your velocity is equal to your bulk modulus for a liquid divided by the density of that material. For a long, slender bar, we use the Young's modulus, because that's what we use in tension and compression back in chapter 10, instead of the bulk modulus. So really, it's just the moduli substituted in there, divided by the density, and that's how you get your velocity. This is your bulk modulus. It's generally a beta, but for some reason the book says BAD, so I just kind of did what the book did. And then this is my Young's modulus, and this is for tension and compression. Not much we do with this. It's just kind of to introduce the equation. It's pretty easy and straightforward. More importantly is sound intensity. Sound waves carry energy. If you're next to a speaker and it's really loud, you're going to know it. And we can actually measure that energy. We measure really the power of a wave, and it's measured in joules per second, of course, in watts. So if I buy a speaker, it's like a 5-watt speaker for my computer. That wattage tells me the power of the intensity of the sound waves that are coming out of it. And we could calculate that by just taking the power divided by the area. And that's measured, of course, in then watts per meter squared or joules per meter squared second. If it emits uniformly in all directions, you get that I is P over 4 pi r squared. This, if you recall from, I think, 2 chapters ago, It's the surface area of a sphere. So what's happening is if we assume you have some sort of sound source and it's emitting in all directions, it's basically emitting in a circle. So this is a really bad idea, the way I drew this. Let's say it's a baby crying, so we're going to do a problem on that. Well, it's going to emit sound in all different directions. So the area would be 4 pi r squared. Remember this in physics 2. It'll come up and you might be a little bit confused on how we were just able to use 4 pi r squared. When we're finding, we use intensity of like electromagnetic waves. Well, this is where it comes from, is that you're emitting it in all directions. Next up, we shall do a problem with said, one thing I wanted to know. So the book kind of talks about this, and it's interesting enough. You could think of it, you can kind of notice the intensity when in the shower, when you're singing. Basically put it, the acoustics, people talk about, well, the acoustics are different. Well, the acoustics in the shower are different and sound more robust because all of those sound waves are bouncing off the walls inside the shower, and you get a more intense wave that is at least perceived by your ear. And it sounds a lot better. So that's why I say people sing in the shower. It could be other reasons too, but and enough that it's worth mentioning. I made this problem last year, so hopefully it's still the best. But this right here is the Soundbox 2. It is the loudest Bluetooth speaker you can buy for a low price. So it was $8.99 last year. I haven't updated the problem from Amazon.com. Anyways, we'll do a problem on it. This is the loudest speaker that we could buy. That's Bluetooth. It has dimensions. It's a 33-pound speaker. It's pretty heavy. Its dimensions are 65 by 43 centimeters. We want to figure out the intensity at a perpendicular point near the surface of the speaker. It's always going to say perpendicular. What it means by that is we know that the speaker is only going to emit from a certain direction. As the speaker I drew in the last example, that wasn't a good example. And so if we're measuring it over here, it's not exactly going to hit it. So the problems are always going to say perpendicular. So at a point like right here. Anywho, it's a pretty easy setup. I is equal to P over A. Now I don't use 4 pi r squared because they gave me an area. So I take my 72 watts, and my area, which needs to be converted to meters, is 0.43 meters, 0.65 meters, and I simply just solve. Next problem will be a little bit more complex, but we'll start easy, I say. And you get 200 and I'm off by a hair. Why am I off by 261? Yeah. So, I know why. The number didn't seem right. 72 divided by 0.43 divided by 0.65. I did 73 on accident. All right. That's going to give me, looks like 258. Watts per square meter as I write meter squared on the bottom. Okay, so pretty simple enough problem. Let's do a little bit one more complex. A man named Fred is near a screaming baby. The intensity he experiences is 5 times greater than his wife, who's standing 10 meters away from the baby. She measures the intensity to be 0.2 watts per square meter. She's always measuring sound intensity when they're in public. Weird. How far is Fred from the baby? Okay, so what we know is that the intensity Fred feels is 5 times the intensity that his wife feels, which I say is IW. That's the basis of what we're going to work with. So what I'm going to do, since we don't have a lot of information, we only have the intensity she measures, we can set up a ratio of IF over IW. And we know I is P over A, so I'll say P over 4 pi RF for Fred squared over P over 4 pi RW squared. The power is the same because it's the same baby. It hasn't changed its power. It's the perception, so to speak, of that power. So power cancels, as does 4 pi. And we get RW flips up to the top, so that's going to be RW squared over RF squared. And that's equal to IF over IW. Okay. Um, then I need to make this a little, or I need to make my substitution here. IF is 5IW, so 5IW over IW, IW goes away, is equal to RW squared over RF squared. We're trying to figure out the radius of Fred, so I'm going to move this around, and we'll say RF squared is equal to 1/5 of RW squared, or RF is equal to the root of 1/5 of the radius of wife. Wife is 10 meters squared. So we didn't actually need to know that she measured the sound intensity unless they asked us another question. But she's weird. She measures sound intensity in public. No, that's not my wife. She doesn't do that. That's something I would do. Maybe. If I had the tools. Yes, I probably would. Anyways, so that's 0.2 times 10 squared is 100. And then I want to rootify that, and I get 4.47 meters. One thing I have to note on this. Let's come over here. All right, 4.47 meters. This, so basically what it's saying is that wife is 2.23 times closer than Fred. Man, husband. I say this because the intensity is 5 times. It's great. But he's only 2.23 times closer. So just because you're half the distance doesn't mean you're going to experience, twice the intensity. It doesn't work that way. What it does work out is that it turns out that the factor by which he is closer, the 2.23, if you square that, you get 5. It's the square of the factor of how closer you are. So when I use my example of half the distance, if you're half the distance, you mean, you're twice as close, it's going to be 4 times the sound intensity, and so forth. So keep that in mind. All right. Okay, decibels. Decibels are more or less a unit of sound, and it's really how we compare 2 different sound intensities. So when they say, the human threshold is XYZ decibels, like 130 or something ridiculous, they're just measuring the relative intensities of like the minimum threshold to like the maximum threshold of the ear. And the minimum threshold for a human is around 1 times 10 to the negative 12 watts per square meter. So extremely, extremely small. Our ears are actually pretty good detectors, amazingly. Eyesight, not so good. We only see in the visible spectrum. And there's a massive electromagnetic spectrum to see in it. We just see a little fraction of it. The dB, the formula. So it's beta again, and that's equal to 10 decibels log of I over I naught. We describe I naught as the basis for human threshold. So pretty much every time this I naught is going to be this 1.1 times 10 to the negative 12 watts per square meter. I is the measured intensity that you're trying to find, and you'll get a unit of decibels. Not really sure the history of it. But decibels is a dimensional unit. That's because you've got watts per square meter divided by watts per square meter, and you got nothing, and the only unit you really come out with is the decibels they just throw on there for randomness. So it's not a true unit, like a radian. And note that the equations will bottom out at 0 if the measured intensity is that of the lower hearing threshold, so that you wouldn't be able to measure any differences. Because you would take the log of 1, and if I put out my calculator here, look for the log button, and then I take the log of 1, oh, holy crap, it gives me 0. So at that, when it does give you 1, but don't forget that the log of 1 is 0. So that kind of throws people off. The smallest a human could detect for a decibel change is going to be around, I think it was 1 decibel um, difference. So the decibel scale, we can supposedly detect between 65 and 64, meaning we know the difference of those two sounds. We can tell the loudness, intensity, well, not loudness, we haven't got there yet, but intensity of those two different sound waves. Most people, done by tests. Well, let's do a problem on it. This one's one of a complicated problem, but the book does one like this, and I think you have one in your homework. All right, fourth time doing this problem now. The other times I got interrupted, and my mouse died, and then my pen died. It's been a whirlwind. But anywho, normal conversation is around 65 decibels, so you can kind of gauge um, the sound level. While the threshold of pain is around 130 decibels. Determine the ratio of IB, which is the threshold of pain, to IA. What I'm going to do is use some of your logarithmic properties that you've probably forgotten from Algebra 2. So I'm going to take beta B, and I'm going to subtract beta A. And we know from the previous slide that beta is nothing more than 10 decibels times the log. And then since it's B, it's going to be IB over I naught minus 10 decibels log of IA over I naught. Now the reason I'm doing this is because if you remember, when you subtract logs you divide, when you add them you multiply. And so what I can do, I'm just going to call this delta B, beta, to make it a little bit shorter, is I can combine them by saying, okay, that's 10 decibels times the log, and I'm going to go IA over I naught over B. I see what you're saying, B, IB. I don't know why I want to write A. I guess because it's alphabetical order. Over IA over I naught. I naughts cancel. That's going to give you 10 decibels times the log of IB over IA. And then that's equal to delta beta. Now, what I'm going to do is plug in some numbers. I know that the delta beta, the change in the 2 decibel levels, is 65 decibels, 130 minus 65. So I could say 65 decibels is equal to 10 decibels, the log of IB over IA. Divide that out. That gives you 6.5. I'm doing this in steps because you may not remember some of this stuff. Is equal to log, so 6.5 nothing. I don't know why I put units on there. Equals the log of IB over I naught. Now, if you recall, IA, sorry. If you recall, when you do log, it's base 10. So you take both sides to you raise both sides raised from the 10th, and so it's 10 to the 6.5 is equal to, and that'll just end up being IB over IA. And then I just take, okay, 10, and I raise that to the 6.5 power of my calculator, and I'm just going to round it, but it's 277. I'm going to say 3.16 million. E6. No units because it's just a ratio. Now, one of the big things about this problem is that the ratio is IB over IA is 3.16 times 10 to the 6th. That's the intensity ratio, but that intensity ratio only equals a doubling because we went from 65 to 130. That's a doubling of the decibel level, but that doubling actually corresponded with an intensity level that did not double. In fact, it is by almost hundreds of thousands of ratios off. So a big thing to gather here is if you double your decibel level, you're not going to double the intensity. Those two are really not related because you're taking the log of it. So remember that. All right, the Doppler effect. Fun times indeed. You probably know about the Doppler effect, at least I have since I was a little kid. There used to be a church over on, I think it's called Hillside Church, amazingly. Maybe. It was on Central and between Webb and Rock. Well, that's not really relevant. But I remember when I would drive by the church, they would have church bells after I went to the Y, and I always drive fast because I always like to hear the Doppler effect. And that's what you hear. It's like, you know, I hear it in a car. It's like, or an ambulance. And that's because of the frequency of those wavelengths, and the frequency of the sources is relative to the velocity of the object. And there are two main Doppler equations, and I'm going to prove at least one of those. And basically, it depends on what is going on. If the source is moving towards a stationary observer, you use the top one, which is F naught, which is the frequency of the observer, over Fs, which is the source. So the source is what's emitting that sound. That's not a good thing. Let's just write source here. And then Vs is the velocity of the source, since it has the S. V is going to be the speed of sound, so that's your 343 in air. And notice that one's a minus, one's a plus, but that's really the only difference between the two. I will show you kind of how that equation comes to be. I have to draw a kind of a pretty picture. All right, so let's say we have a person right here. All right. And they're just hanging out, beating themselves. And he's thinking, and he says something. He says, popcorn. Because that's what people do. And then we have a person, and there's a wall over here. I drew this ahead of time because I suck at pictures. And he's just hanging out next to the wall, being a wall person, stud, if that's something. And he's thinking too. He's thinking. And that's my observer. And we know that the distance between them is going to be lambda. Well, this is if he's stationary. If he starts moving, then things change a little bit. So we have a runner, and he is running, and he's now saying cheese, you know, because cheese popcorn. And the observer is still there, hanging out, you know, being the best observer he knows how to observe. All the same. Now, when you're moving, there's going to be a little bit less of a wavelength that we'll call lambda prime. And also, there's going to be a little chunk that's going to depend on your own velocity. And that is the velocity of the source times the period. And you're thinking, oh, that doesn't look right. You know, velocity times time. Remember, it's a little bit different in this regard in how we're dealing with it. So, because that's the... sorry, I got... someone walked by. It's the velocity, and you're marching by the period, but remember, we want a unit of displacement here. And so the velocity of your source is in meters a second, and then your period is in seconds, and so that ends up being the same unit as the top picture. So it's going to be shortened by a little bit. Well, a couple things we do know. Let's walk over here. We know that Fs is equal to V over lambda, because we've learned that already. V equals F lambda, flamda, and so we're going to utilize that. And that's our source. And then for our observer, see if I can fit this in here. I hope so. It's going to be a little bit different. It's going to be our velocity over what we see to be as lambda minus the VST. Basically put, this lambda is what it would be if they were, stationary. such as up here, but they're not. They're not stationary. They're moving, and so it's going to be a little bit less of a distance it has to travel, less of a distance by a factor of VST. Now, I know a couple of things. I know that lambda is equal to V over Fs. And I also know that t, the period, is 1 over Fs. And so I'm going to make a substitution. Let me go down here. I should have some room here a little bit. I'm going to erase my picture because I don't really need the observer anymore. All right, so that's F naught equals V. The lambda is going to be V over Fs. And I'll put this in parentheses to say, hey, I made that substitution. And then this is going to be Vs over Fs. And I made the period substitution. Now notice I can pull out the Fs. And it's on the bottom, so we could flip up to the top. And so I can say Fs, and then that's going to give me inside of this V over, looks like V minus Vs. And then if I divide both by V, the bottom and the top by V, right over here, you get this. Run out of room. Let's erase all this. Should have left myself more room. I didn't anticipate that. Bad of me. Well, normally I write this on a board, so yeah. All right, so giving that, it gives me F naught. We pulled out our Fs. We divided everything by V. And so that's going to give me Fs 1 over 1 minus V over Vs. Because we divided, that's not a Vs. We divided everything, or divided multiplied everything by V. Vs over V. I know I just did something wrong. Sorry. Vs over V. And I didn't do that right. Well, I did it right, but it didn't look good. All right. Doesn't look too clean, but anyways, that's kind of where the equations come from. It's just basically looking at the structure of what's going on. It's not a magical equation. It's just, doing some little bit of arithmetic and math, and we come out with both those equations. Not necessarily both, but depending on the situation, we can work backwards to get that. So we know a couple things. And one other thing I need to point out is that sometimes you hear something called the Doppler shift. And the Doppler shift is basically finding the difference between the two frequencies, the observed minus the source. But anyways, we'll get to that here in a little bit, but that's something I have on my notes for you to point out. All right, we have an Australian raven. I went to Australia, not last summer, but 2 summers ago. No one went anywhere last summer. But they are interesting in that they have a ridiculous call. It is very, very odd. It sounds like a little child. I thought it was. My wife changed it to her cell phone, and there's a cat in our house. It's not even our cat, but he does not like that sound. He goes crazy. Anywho, that's the Australian raven I did a problem about. And it could travel at speeds of around 50 miles an hour, 22.3 meters a second. It's kind of its top speed. The speed of sound we'll assume is 343 meters a second, and the emitted frequency we'll assume is 510 hertz. We want to know the perceived frequency and the wavelength of sound if the raven is coming towards the observer or moving away from the observer. And then we also want to figure out what is the observed wavelength. Okay. All right, so we've got F naught is going to be equal to Fs, and then that's 1 over 1 minus Vs. Oopsie. I'm struggling writing Vs over V today. Sorry about that. Vs over V. And if we look back, that is the moving towards the stationary observer, and it says moving towards the observer, so we're using the right equation. I just need to plug in to get my answer. It's pretty simple. So I will do that as soon as I find my cursor. There we go. F naught is equal to the frequency of my source. So the source is the crow, and so since the crow is 510 hertz, that's what I'm going to be using. And then times 1 over 1 minus the velocity of the source. So that the source is the crow, so it's the velocity of said crow. And so that's going to be 22.3 meters a second. And then we divide that by 343 meters a second. And then calculation time. So I'm going to take 22.3, divide that by 343, and I'm going to take 1 minus that number, and then I'm going to divide that into 1, and then I'm going to multiply by 510, and I'm going to get 545. All right, so, and then you can kind of check yourself. If something's coming towards you, then it should be getting higher pitched, higher frequency, and that's exactly what's happening. It's 545 hertz. So it actually works out. Then it says, okay, well, what happens when it moves away from the observer? So we'll do kind of the opposite equation over here. And so that's going to be F naught is equal to Fs times 1 over 1 plus Vs over V. So the real difference is the plus and the minus. Okay, so F naught is then going to be my 510 hertz. And then, ooh, that's ugly. 1 over 1 plus 22.3. I'm going to leave off the units since they're going to cancel anyways. 343. Alright, so I do 1 plus, so actually let's just do 22.3 divided by 343. I'm going to add that to 1, and then I'm going to take 1 divided by that answer. And then I'm going to multiply that by 510, and that's going to give me 479. We're going to round it. And so if it's moving away, it should drop in pitch according to the Doppler effect, and indeed it does. It drops to 479. It also says, well, what is the observed wavelength? And that kind of comes from earlier, coming from the proof. But lambda prime was, I think I erased it. I did. Sorry. That was the observed wavelength. And that's actually nothing more than the velocity divided by your observed frequency. And so I just plug in. As soon as I can figure out where my room is. Running out of room on this. Alright, and so that's going to be my 343 meters a second. And then my observed wavelength was 479. Yeah, it's right there. And so 343 divided by 479, and that's going to be 0.72. And just a little bit of a refresher here. This observed wavelength comes from, dang it, I thought I had that up there. This part right here, because I talked about how we had right up here, we had the VST at one point. And then we had this lambda. Well, that VST, that's what we're kind of utilizing there in that regard. And up here, we know that lambda is equal to V over Vs. The lambda prime would be V over F naught. That's how we can get that perceived wavelength. Okay, moving observer. There is a proof for it, but since I proved one of them, it just gets kind of messy pretty quickly. But I kind of show you a little bit about it. For a moving observer, we have two equations. It's a little bit more complicated, but we have F naught is equal to Fs 1 minus V naught over Vs. And then we have F naught is equal to Fs 1 plus V naught over Vs. If we put both of them together, we can create kind of a master equation. You'll see this, I think it's what, chapter 28, I think, in Physics 2, when you start looking at the Doppler shift of like light. So I kind of more use this equation than the other top two, which is just an amalgamation of the two equations. But I can kind of give you an idea of at least where it comes from. Okay, what we can do this, we'll start with this. We have F naught, the frequency of the observed. It's going to be Fs plus some velocity, which we'll call V naught, over lambda. This will be the frequency of the source, and then we know that the velocity, meters per second, divided by the lambda, meters, is going to give us also a frequency. One thing to note, that the wavelength actually does not change. What is changing, because it's a constant there, is the actual intercepted condensations, if you remember back from a couple of slides ago. Okay, well, I have kind of something to at least start with. I know that lambda, it's a bad lambda. I know that my lambda is, funny, is equal to V over Fs, and I think that I said that way up here at some point. Lambda equals V over Vs right there at the top. And so I can make a substitution. So that's F naught is equal to Fs plus, and then this will be V naught over, then V over Fs. Fun. And then that's going to reduce to F naught is equal to Fs plus Fs, V naught over V. And so when you pull out the Fs, surprise, surprise, you get, at least in this case, this equation. So when you're moving, you have to take into account you have the frequency of the source. But since the observer's moving, that's why we have this little second part right here, because we're taking into account that not only is the source moving, but we also have the observer moving as well, which is why there's a second part to that little equation. Minus is pretty much the same way, at least proven-wise. And putting them together is kind of more or less just arithmetic, but I'm mostly going to focus on this equation right here. There are 4 situations, and I'll write that out for you. I'm going to erase this. And I don't normally use these situations, to be honest with you, but let me write them out first, and then I'll tell you what I do. We have, okay, so in the numerator, it'll be positive if the observer, I'm just going to call OBS, moves towards source, and it's going to be a negative if the observer moves away source. And then for your denominator, it will be positive if observer moves away source, and then negative if observer moves toward the source. All right, so 4 different situations. You could kind of memorize that. Honestly, what I do, I don't know why I do it this way, but I guess it's easier for me. I think about the situation. So if I see that a truck is honking its horn and moving towards me, then, okay, so if the truck is moving towards me and I'm driving toward the truck, that means the frequency that I'm going to detect is going to be high, like really higher, much higher, since we're both moving. And so I want to maximize this value as much as possible. And the only way to maximize that is to have a negative on the bottom and a positive up top. That way it maximizes the biggest value that I can get in order to accommodate the appropriate frequency. So what I do is I usually think about the situation and say, do I need a higher frequency or do I need a lower frequency? and then I adjust my negative and positive signs based off of that. If it's not moving, if one of them is stationary, well, then we can just go right back to these top equations. But when they're moving, you can usually use this, and it works its way out pretty easily, at least in my opinion. And if one of them is indeed, say, stationary, let's say your observer is not moving. If your observer is not moving, then this whole argument right here is 0. And then we get 1 over 1 something Vs over V. And then if I go up to the top right here, I see 1 over 1 plus Vs over V. So the equation actually collapses. So this, to me, is the master equation to use. I can use this to get all of my instances out. And to be honest, I will forget on multiple occasions which equation is which. I every time tell myself, are they moving? Higher frequency, lower frequency. That way I don't have to memorize the equation, because I hate memorizing equations. I either build them myself or, yeah, I just don't like memorizing equations. And this makes my life easier. It makes more sense to me too. If you can't do it that way, it's fine, but it does help you understand the situation better. All right, so let's do a problem. I've always been fascinated by this, but the first ever submarine was actually used during the Revolutionary War. This is a replica of the Turtle, which is what it's called. It is not on U.S. soil. It's actually in a submarine museum in the U.K. And it was attempted to be used against the British. Fun fact. It didn't really go anywhere, and you didn't really have much navigation, and it was kind of terrible, and it wasn't really successful, but it was a submarine, and it did go through. What they didn't account for, I think, was the current, and they couldn't. It was a pedal power. They couldn't fight the current. Excuse me. Anywho, all right. So the first ever submarine was used by the Americans in the American Independence War. Assume that the sub is moving towards a British ship at 3 meters a second, while the ship is moving towards the sub at 6 meters a second. Very slow, I know, but this is back in the Revolutionary War. Things didn't move too fast. If a sound is emitted by the sub, let's say, some sort of squeaky squeak at 1525 hertz, and at 1500 meters a second, then what is the frequency detected by the ship? Then we'll say the pulse bounces off the ship and returns to the sub. What's the observed frequency detected by the sub? Okay, so let's write out my equation here. I left myself room on this one. Yay for me. Don't always do that, do I? Nope. So we have F naught is equal to Fs 1 plus V naught over V over 1 plus Vs over V. Closing parentheses. Okay, so it's moving towards it. Since it's moving towards it, and they're both moving towards each other, then I know that the frequency is going to get higher. So I know that it's going to be positive up top and negative on the bottom, since they're both moving towards each other. That way we can increase the value the most. If, let's say, my American sub was moving towards them, and then the other sub was moving, and the other ship was moving away, then I would make this bottom positive, or vice versa. So that's how I do it. I kind of just think about the situation and work with it based off of this formula, and all I have to do is remember that equation. But anyways, so I'm going to use that. Let's do that. So F naught is equal to 1525 hertz. Then that'll be 1 plus 6 over 1500. Why am I using 1500? I wasn't quite clear because I was running out of room. This is the speed of sound in water. So this will be V water. Excuse me. So that's why it's 1500. I should have been more clear, but I was running out of room on the slide, and I wanted to there's just too much good information when you talk about submarines used in the Revolutionary War. I mean, man. All right, so then 1 minus 3 over 1500. Calculator. All right, so 1 plus 6 divided by 1500 divided by 1 minus 3 divided by 1500. and multiply that by 1525. And I get 1534. Not much higher, but definitely higher, which makes sense because they're moving towards each other. Now, the fun part about this is the pulse bounces off the ship and then returns to the sub. So, you see those movies and they've got like the sonar going off and, pew, pew, pew. What's its detection? So we use the same equation. It's actually the same exact setup. It's that your frequency of the source is now going to be the observed from the beginning, because since it's bouncing off the ship, that now becomes the source. So the ship is the source. And it's going to send back to you a wave that is 1434 hertz. So that's fun. And we do have a little bit of a shifting now. This will be 3 over 1500, since the 3 corresponds with the ship. So we need to use the 3 here because the observed is now the sub, and the sub was moving at 3. And then on the bottom, we have the source, and this source was the ship, and it was moving at 6 meters a second. So everything else should roughly stay the same. And, except for the fact that I put a plus on the bottom here, and I meant to put a minus. There we go. Okay, so we have 3 divided by 1500, and I'm going to add that to 1, and then I'm going to divide that by 1 minus, and then take 6 divided by the 1500, close, close, double parentheses, multiply that by the 1534, and I will get 1543. So that's kind of interesting, at least to me. If it sends out a ping at 1525 hertz, it's going to return at 1543 hertz. So it's kind of weird, but it's kind of like an echo, but instead your echo sounds muffled, not muffled, but off. Your pitch has changed. It's like, someone with a really deep voice. I can't think of anybody off the top of my head that has a really deep voice. Ivan Moody from Five Finger Death Punch has a bit of a deep voice. He would be talking and he would hear himself with a higher pitched squeaky voice, which is kind of cool. But anywho. All right, well, that is it for Chapter 16.